So we have been yesterday. We arrived at how we can solve, how we can find eigenvalues for eigenstates, and there is a particular way or procedure by which we can determine eigenvalues. So it has an analogy with the classical, how we solve the classical secular determinant equation in linear algebra. तो जो हमारी it overlaps, the methodology overlaps with how we find things in the linear algebra and how we see matrices, how we solve those secular equations. So in the same context, we are that procedure had some overlaps with how we try to find eigenvalues. Now in today's class, and at the end, we arrived at something called that. So whether eigenvalues can be repeated or not, it depended upon when n is equal to 1, 2, n minus 1. So whatever. So for any repeated eigenvalue, so the procedure is equally applicable whether or not there are repeated eigenvalues. So in today's class, what we are going to see first, we are going to prove that eigenvalues ui prime of the unitary operator have property ui square is 1. So you can see it. जो हमारा u dagger u, if it's unitary operator, it has u dagger u is 1, u is equal to u inverse. So here, since it's Hermitian operators, so you can have u dagger u, you can have u square, also ui square is also 1. So but we are going to use हम इसमें bracket formalism का, we'll take recourse to that. So we know in bracket formalism or notation. Yeah, notation is a better word. So eigenvalue problem for the normal operators can be written as or it appears as, so you can have ki, kj, el prime. So you can always see this kj, it's bra and cat, it will be equivalent to 1. So it's ki of a of al. This is component of this in terms of this. You can write it as al prime, k of al prime. So you can say this and this is equal to 1. You can also write it like this. Or ai prime or al prime. So if I is not equivalent to L, then it's equivalent to delta IL. So I is equivalent to L is 1, I is equivalent to L is equivalent to 0. So for, if we have a definition, अगर आप याद रखिए, if you remember, हमने projection operators को ऐसे define किया था that if you flip the sign, the projection operators, it will things will come back. So such that if I is equivalent to 1 to n, so we can have defined as sigma I is equal to 1 to n, P of I is 1. So P, this is what I should say, projection operator for eigenvector AI. So a transformation matrix S with matrix elements can also be defined as SRL AL. So it's I and it's L. So a transformation matrix can also be written in terms of this bra-ket notation. Here you can see there are two indices I and L. So you can take bra has one indices, ket has another indices. These bras and kets can be two matrices, rows and columns. You can say it in that sense. And operator acting on this thing may lead to row, and if it's column, it may go to row if it's being externally acted upon by an operator. Then operator can itself be matrices with having components ig. So there is always a procedure by which you can go from bra to ket and ket to bra via some matrix transformation, which you have done previously. So if you use this understanding, you can have I of j, this is a and a prime, ki, a, kj. So if you want to write it in terms of ki, kj, so you can write it like that. So AL prime delta ln. So we have written, so ki, you can always say it's 1. kg is 1. So you can have, this is AL. You can write it as delta ln. So this is our A. That's it. So either 10.15, 10.15 is this. So or 10.19. So if these two things, these two you can, so here you can have only I and in terms of only one components. Here we have ki, kg. So either we can use this or you can use this equation to calculate, to determine components of eigenvectors. Now we are coming back to जो हमारा जो idea of similarity transformation है. So हम एक particular matrix property use करके and operators को we are going to betwixt between those operators via those properties of similarity transformations, and how see how हमारी जो eigenvalue problem है, how it will pan out, or how we can write it. So we know that A inverse is equal to S inverse A of S. So what we are doing is basically we have to prove eigenvalues of unitary operator or going to have this property. Okay. We know that जो unitary operator है उसकी property है u dagger is equal to or u inverse is equal to u, है ना, this we know. अब now we have to see it in terms of bracket notation. So bracket notation में ये है कि this is ki kj, so we can write components of a given vector. ठीक है, तो हम ऐसे भी रिप्रेजेंट कर सकते हैं. Where you can see this ki kj है ना, ऐसे ki kg, ये है डेल्टा ij. If it's equal to kg, then it's equal to 1. So you can write it ki, components of ki in terms of ai, al ऐसे, ठीक है. But it's mediated by this bracket kg. And again we have defined projection operators को हमने ऐसे define किया है that if you project projection operators are such that it will get the state back to its original state, ठीक है. Such that ai कितनी बार भी projection operator acting, it will get the state back such that at the end it will have some normalization condition, ठीक है. अब ये हमारे पास ये तो एक components को हमने यूज किया. We can also use two components here, ठीक है. Here we have used kg. Now we can use ki, kg, ठीक है. Again it's also equivalent to 1, it's also equivalent to, so it's inner product of the same vectors है ना, ऐसे ki, kg. It's basically आपका वो वाला inner product of psi star. Psi star is equivalent to 1. You can also, this is the bracket way of writing the same thing, ठीक है. Inner product of two states, ठीक है. अब ये inner product of one states है, inner product of two component states. अब I also previously said the bra is nothing, so we can convert a bra को या एक स्टेट को हम कन्वर्ट करते हैं, ब्रा को कैट पे कन्वर्ट कर सकते हैं, कैट को वाया सम मैट्रिक्स ट्रांसफॉर्मेशन, वाया सम मैट्रिक्स. जैसे आपके पास रोज है ना, दिस इज a1 a2 a3, दिस इज b1 b2. सो आफ्टर ये रो है ना, if you multiply it by column after matrix multiplication, this row will also translate into column, है ना. इसका multiplication क्या है, a1 b1 plus a2 b2 plus, है कि नहीं, आया कि नहीं. So I have multiplied this state with, you can think of bra as row and cat as column vector, ठीक है. So an operator acting on bra will change it into cat and vice versa. A cat will change into bra, but you can mediate the same through some operators. And operators have something called, they have property similar to that of as if we are transforming matrices, ठीक है. So such that we can always translate. अगर हमारे पास psi I है ना, aij aik j हाँ ऐसे. So you see psi I को है ना ये matrix, j will come cancel, ये psi I आएगा, psi is equal to psi. So you can always go from psi I to psi j via this 2 cross 2 matrices. But this 2 cross 2 matrices will be some operator. Got my point? अब ये है कि जो हमारे पास यहाँ bra cat notation है in that sense. So what I want to connect it in our yesterday's class. Yesterday's class में हमने क्या किया था? We have found at the end solution of eigenvalues. Eigenvalues को कैसे निकालते हैं या eigenvalue problem कैसे solve करते हैं? For a given eigenstate, it will map to a unique eigenvalue. उसका कोई value eigenvalue आएगा. So that tantamount to at the end we are solving a sort of matrix equation, secular determinant निकालते हैं. ऐसे हमने last में पूछे थे, ऐसे determinant of aij minus lambda delta ij is 0. फिर हमने कहा था कि ij is 1, तो उसके फिर n, जब n लीनियर इक्वेशंस होंगी उसके n सॉल्यूशंस होंगी, इसी तरह n आइगन वैल्यूज होंगी, ठीक है. सो दैट्स, अब वही एक्सरसाइज वी आर डूइंग इट. you have to prove that eigenvalues of a unitary operator have this property. We are going to do this. तो यहाँ तक तो हम पहुँचे ना. So this point we have reached here. Now we are going to use properties of similarity transformations in matrices. कोई भी matrices को आप in terms of एस इनवर्स एस लिख सकते हैं। आप इसको पहले एस इनवर्स से मल्टीप्लाई करो ए को, फिर उसको एस मैट्रिक्स के, सो इट विल बी एस बैक, यू विल कम टू ए विल बी इक्वल टू जो हर्मिशन प्रॉपर्टी, बिकॉज वी आर इंटरेस्टेड इन हर्मिशन ऑपरेटर्स। हर्मिशन ऑपरेटर्स में ए इज इक्वल टू ए डैगर, है ना, एंड दैट विल अल्टीमेटली हर्मिशन ऑपरेटर्स में भी यही प्रॉपर्टी आती है, ठीक है, इन दैट सेंस। So we can use the property of similarity transformations, which will help us to determine the eigenvalue states, जो हम कहते हैं ना, they have the property this. So eigenvalue property क्या क्या आएगा? If A is equal to this, determinant of this is A कल वाला, this is lambda ij, I is equal to j, this is determinant of A minus lambda. Lambda into I is unitary transformation. You can multiply any lambda with I, it will get you back. So you are going to use this property of similarity transformation here. A minus lambda I into S. Or again, determinant of A minus lambda I will be equal to 0, कल वाली जो सेक्युलर डिटरमिनेंट इक्वेशन हमारे पास है। So again we are going to use another property. If you know determinant of AB is determinant of A, determinant of B, ठीक है। Now we are going to use these two properties here, A minus lambda I. अब लैम्डा आई हमारे पास एक भी है, ये लैम्डा 0 भी है, लैम्डा 1 भी है, लैम्डा 2 भी है, सो लैम्डा n माइनस 1 भी है, एंड लैम्डा n आइगन वैल्यूज का जो हमारा डिटरमिनेंट आ रहा था हमारे पास a00, a11, a12, a13, a1n, a00, a11, a01, a02, a0, a10, a11, a12 ऐसे, ठीक है। तो उसका हमको निकालना है n आइगन वैल्यूज इन टर्म्स ऑफ सॉल्विंग दिस इक्वेशन। सो वी आर गोइंग टू यूज दिस प्रॉपर्टी एज दिस प्रॉपर्टी ऑफ सिमिलैरिटी ट्रांसफॉर्मेशन। सो हमारा जो सॉल्यूशन आएगा, सो वी कैन ईदर यू डू द सेम प्रॉब्लम बाय योर अंडरस्टैंडिंग ऑफ लीनियर अलजेब्रा, ठीक है, बट we are doing the same by that matrix method also, but we have an understanding of operators. Operators may not necessarily be matrices, ये याद रखना, क्योंकि जो operators है ना, they act on state psi, and psi state है ना, ये infinite dimensional Hilbert spaces को कहते हैं ऐसे, जिसमें eigen value के eigen states when they are acted on operators, they will have these values on this space, which will be discrete as well as continuous, ठीक है, जो यहां पर लाई करेंगे ऐसे ऐसे ऐसे, ठीक है, एंड दे शुड बी नॉर्मलाइज्ड psi स्टार एंड बाउंडेड यहां से यहां तक। यू आर बेसिकली ट्राइंग टू फाइंड इवोल्यूशन ऑफ वेव फंक्शन psi, ठीक है, इन दैट सेंस। सो जो मैट्रिसेस में हमारी अंडरस्टैंडिंग है, जो प्रॉपर्टीज ऑफ मैट्रिसेस या डिटरमिनेंट्स है, सो इट कम्स समटाइम्स हैवी, यू कैन replace operators by matrices, but not always, because sometimes जो basis vector है in case of operators, it may vary from basis to basis, ठीक है, तो वहाँ general matrices के लिए होता है। So this is the thing. So that's why here जो हमारी जो similarity transformation है, so we have to see कौन सी basis है for our operators. So जो इसका solution आएगा for different n, it will be trace of a n minus 1, फिर n minus 2, फिर n minus 3, and फिर n minus n, वो 0 आएगा, it will be determinant of a. These are solutions of this equation हमारे पास जो आएगा for different values of a. अब ये trace क्यों निकाल रहा है? Sometimes जो ये है ना, जैसे a00, a11, a12 है ना, ये a1, 01, 02, 10, 11, 12, तो मे बी ऑफ diagonal elements sometimes you can take if they don't contribute. If they don't contribute, तो simplest cases में हम कैसे we will take the trace will be the solution of this thing. ठीक है, that's it. So अब ये है कि you can always show that trace of A B. अब कोई भी मैट्रिसेस का लोगे आप ट्रेस लोगे, मैट्रिक्स A लोगे, मैट्रिक्स B लोगे, you just see at your place trace of AB will be equal to trace of BA, या trace of ABC is equal to trace of, you change the order, BCA, CAB, trace of BCA, or trace of A is equal to trace of S inverse AB. So we are going to use similarity transformations here. Trace of A. So the point to mention is we are going to use A property, a determinant of A, this cyclicity of trace, A property to solve the eigenvalue. Eigenvalue को कैसे निकालना है for different n's. So for simplest cases it is like this. And if you want to so you can, अभी कह रहा है कि it is legitimate मतलब क्या हो गया? Legitimate मतलब you can replace जो operators की matrices की definition को in terms of operators A, operator है ना A. So मैंने कहा था always operators and matrices may not coincide, but we can, using this exercise, we can take matrices as operators. If it is that way, we can say that for a normal operator, trace of A is equal to A1 plus A2 prime plus AN. So it is sum of eigenvalues of A. This is an eigenvalue problem. How we can determine eigenvalues for a particular determinant. So it ultimately basically boils down to adding the जो इनके diagonal elements हैं different matrices, ठीक है? Or you can use another property, determinant of A is equal to A1 prime cross of A2 prime cross of, and it's the product of eigenvalues of A. And further, अगर हम इसको matrices को देखते हैं, you can see mathematical physics, Baker-Hopf-Pursdorf formula एक है. You can further simplify it in terms of, अगर इसको determinant को in terms of exponential form लिखें, determinant of A, ठीक है ना? E to the power A1 plus x square by 2 factorial, so on and so forth. So it will be 1 plus A by 1 factorial, A by 2 factorial, plus so on and so forth. और इसको थोड़ा सा सिंप्लीफाई करेंगे, लिमिट n tends to infinity 1 plus A by n. And in the same way you can write determinant of EA. Again we are writing this multiplication form here as exponential of sigma phi AI, exponential of trace of A. So what we have done is basically these cyclicity property, this property and similarity transformation को use करके इसको इस equation में डाल के, this is basically solution of this equation, yesterday's equation. How we can determine the eigenvalues. Eigenvalue problem क्या होता है? Eigenvalue problem को कैसे solve करते हैं? ठीक है? For state psi. And at the end we have done this. अब इसमें ये है कि sometimes we can have other procedures also. So it is for general n, n1, n2, n3, n. ठीक है? अब थोड़ा सा हम कहते हैं ना, जिस तरह हम approximate methods use करते हैं, ठीक है? We are going to use so if it's for general n, तो ये थोड़ा problem बन जाता है ना open ended. So we want a problem to be solved with some well-defined boundary conditions, जिसको हम कहते हैं boundary value problem. जैसे ये Electron has started moving here and it will stop here. So we have used some boundary conditions. Yeah, for particular eigenvalues only, n is equal to 1 and 2 देखेंगे हम, ठीक है, which will correspond to some states. और in terms of अगर energy operators हम देखेंगे, it will correspond to some energy. If you remember, हमने हार्मोनिक ऑसिलेटर के लिए क्या किया था? इक्विलिब्रेशन along ground state. First two orders of perturbation हमने देखा था, उसकी एनर्जी क्या आएगी, ठीक है? For n is equal to 1 and n is equal to 2. So we can, our problem is जो ये हमारी आइगन वैल्यू प्रॉब्लम है, it's for general n, ठीक है? तो we want to restrict it to some suitable n with well-defined boundary conditions, boundary value problem जो है कहते हैं. There are various methods. For example, how can, if you just go to the book, so there is a method we have discussed, eigenvalue problem for a bounded Hermitian operator. ठीक है, कैसे करेंगे? For any desired approximation, because we are using Hermitian operators, है ना? H is equal to Hermitian operators use करके, तो हम कैसे eigenvalue problem for first few orders of perturbative expansion लेंगे, ठीक है? So this is our, so that हम हमारा काम आसान हो जाएगा. Got my point? We are not going to solve for general n, we are going to solve for some orders of n. Yes, that's it. So हमारे पास if I just हमारे पास I just only say क्या है ये so हमने कल कहा था operator operating on this is A और psi and lambda psi को हम define करेंगे for lambda naught. If you remember, this is psi naught A psi naught divided by psi naught psi. This is component of that state in the given direction. So psi naught आएगा psi square, it will be 1. ठीक है? So what we are going to do, this is what we are going to do. Lambda psi naught plus minus epsilon phi is greater than or equal to lambda naught. So we are going to change psi naught to हमारा first wave function, psi 0, psi 1, psi 2, psi 3, and these are different eigenvalues. So we are going to change some epsilon phi के हिसाब से इसको देखेंगे, ठीक है? Epsilon may be 1, 2, so small changes, and we are going to operate it along such that so if we substitute it here, so we have this equation. इसका फॉर्म ऐसे आएगा, epsilon q is less than a minus lambda psi naught plus psi of a minus lambda naught phi naught. So this is, it will have a solution from this epsilon q and well, जो मैंने कहा था बाउंड्री वैल्यू प्रॉब्लम, ठीक है? यहां से यहां तक इन दो के दरमियान जो ये सॉल्यूशंस है ना, a माइनस लैम्डा है ना, ये a माइनस लैम्डा नॉट a माइनस लैम्डा नॉट. So it will be bounded between this epsilon theta and it will be less than or this or greater than this. इसके दरमियान the way we solve it for real world problems. और हमारा जो दूसरा मेथड है उसको कहते हैं ग्राम शुल्क ऑर्थोगोनलाइजेशन मेथड, जो हमने किया था, दैट या वी लीव इट दैट. सो हम क्या कहेंगे काम, सो जो आइगन वैल्यू है इट मे बी ग्रेटर देन लैम्डा और less than minus infinity. ओके वी लीव इट हियर. ये थोड़ा सा डिस्कशन इट रिक्वायर्स थोड़ा सा इसमें रिलीज एक दूसरा मेथड है एज एन अप्रोक्सीमेशन. अब एटलीस्ट एज एन आइडिया ही हमारे पास ये है कि इन आवर क्लास व्हाट वी ट्राई टू फाइंड इज जो हमारा यस्टरडेज हाउ वी कैन फाइंड द इस सर्कुलर इक्वेशन को कैसे हाउ वी कैन फाइंड द आइगन वैल्यूज. दोज आइगन वैल्यूज correspond to the eigen states which are acted upon by some operators. अब जो आइगन वैल्यूज निकलेंगे उसके लिए हमारे पास जनरल एन सर्कुलर इक्वेशन सॉल्व करनी पड़ेगी. उस सर्कुलर एन इक्वेशन को थोड़ा आज के क्लास में वी ट्राई टू शो विद सम प्रॉपर्टीज ऑफ द साइक्लिसिटी ऑफ ट्रेट्स डिटरमिनेंट ऑफ ए इज इक्वल टू दिस यूज करके थोड़ा उसको हमने सिंप्लीफाइड फॉर्म में लिखा एंड इट केम आउट टू बी दैट सॉल्विंग आइगन वैल्यू प्रॉब्लम इज एज इफ यू आर एडिंग द ट्रेस ऑफ दोस वी हैव सिंप्लीफाइड इट इन सम सेंस. ठीक है, स्टॉप.